And so we say a fond farewell to our discussions on ionic bonding. So one more look at an ionic compound there, our positively charged cations and our negatively charged anions joining together to form an ionic compound. I now want to spend the next few topics talking to you about covalent compounds. These happen when two atoms share electrons with one another. It tends to happen typically between one nonmetal and another nonmetal. Now I've got your periodic table up there in front of you and it's color-coded, and you can see that the nonmetals make up a very small portion of the periodic table. So I couldn't blame you for thinking, well, how important can this be? It's only a tiny bit of the periodic table. This could not be further from the truth. Lots of the materials around you are actually made up of this very small selection of elements. Well, we can start with one we've already discussed. Water is made of hydrogen and oxygen. Remember, hydrogen is an honorary non-metal. But if we look around, what else have we got? Plastics are made primarily of carbon and hydrogen, often oxygen, nitrogen, and sometimes things like fluorine and chlorine to give them some interesting properties. Fuels that we use for all kinds of transport are made primarily of carbon and hydrogen, also sometimes oxygen. Fats, oils, proteins, carbohydrates, vitamins, food, glorious food in general, primarily made up of carbon, hydrogen, oxygen and nitrogen. If we move out into nature, the trees, the plants, the grass, that's all carbon, hydrogen, nitrogen and oxygen. We are made, well, we're 70% water, so that's hydrogen and oxygen, and the other two major components of us are carbon and nitrogen. So you can see that you, me and many things around us are actually made of non-metals. So despite the fact that it's a very small part of your periodic table, it makes up a big part of our lives, which means understanding how these atoms unite and bond with one another is a really important thing for us to be able to do. Once again, a bit of a reminder, when do we get covalent compounds? When do atoms decide to share rather than form ionic compounds? Usually non-metal and non-metal, and we can use electronegativity difference as a guide. So we're now talking about situations where the difference in electronegativity between two atoms is small, less than 1.6. Do you remember what electronegativity is? It's a measure of how much an atom wants to take those electrons as part of a chemical bond. So if the two atoms that are uniting have similar electronegativities, they both want those electrons. It's not going to be give and take. The only way this is going to happen is if they share. Now within this region, this electronegativity difference being small between 0 and 1.6, I want to rule another line inside that area because it will also distinguish some of the properties some of these new compounds we make will have. On your screen, I've got a couple of example molecules that we're going to use to discuss these differences in electronegativity. Don't worry about how to draw the molecules, we'll talk about that in the next couple of topics. Let's focus on the top one first, the CH4, the methane. If you have a look at the two atoms that we're using to build it, the carbon and hydrogen, in particular their electronegativities. Carbon has an electronegativity of 2.5, hydrogen 2.1. So their electronegativities are quite similar. In particular, I'm drawing the line at 0.5. The difference is less than 0.5, and that means we call it a non-polar molecule. What does that mean? It means that the electrons are shared quite evenly right throughout this molecule. There is no great distribution of electrons in any one part as opposed to another. As opposed to the opposite, let's have a look at the bottom example. Let's have a look at water. If we look at the electronegativities on the oxygen and the hydrogen, oxygen is 3.5 and hydrogen is 2.1. Now, the difference between them is 1.4. That's less than 1.6, so this will be a covalent bond. They will share electrons, but it's more than 0.5. And that means that while they are sharing, there's no question that oxygen wants those electrons more than the hydrogen. And that means that oxygen is going to be a little bit greedy. It's going to pull those electrons towards one end of the molecule. So the electrons will be pulled in this direction, towards the oxygen and away from the hydrogen. And that's why I've used these two symbols here. The symbol at the top, delta negative is how we will pronounce it. It means slightly negative. The delta plus means slightly positive. We now have what we call a polar molecule, where one end is a little bit negative and one end is a little bit positive. So it's good for us to be able to pick out non-polar molecules or polar molecules, polar covalent molecules, because they do behave differently and they interact differently with one another. In Module 3, when we start discussing chemical reactions, being able to differentiate between these two will be important. So, in the next few topics, we're going to talk about how to draw these covalent compounds, But just quickly before we get into that, I want to talk about how to name these covalent compounds when electrons are shared. Some of the rules are similar to ionic compounds, but there are a few key differences. If you look at your slide that I've got up and present for you right now, you'll notice that I've got some prefixes across the top, some numbers and words to go with them. That's because unlike ionic compounds, where we simply name the cation and then name the anion, when we have covalent compounds, we do need to be a lot more specific about how many of each atom we have. And that's because we can often join two individual elements in a variety of different ratios. And I'll show you an example of that in just a moment. So we need to use these prefixes. And we've got prefixes for many numbers, but for us, I'm happy with just going from 1 to 6. So if we've got one of an element and we want to be very specific about it, we can use the prefix mono. More often than not, we just don't use a prefix at all. For 2 of an element, di. 3, that's tri. 4 is not quad. That's what everyone wants to say. The prefix for 4 is tetra. For 5, it's penta. And for 6, it's hexa. So let's try and name these compounds that we have here. So for the first example, CO2 will go right through all the rules. We name the first element first, and it stays exactly the same way it is. So C for carbon stays carbon. The second, or the last element, we change the ending to "ide", just like we did for the ionic compounds. So oxygen would become oxide, fluorine would become fluoride. But now we need to get across to our person we're communicating with, to our fellow chemist, that there are 2 oxygens. So to tell them there's 2, we use our prefixes. We put the di prefix in front. So this would be carbon dioxide. Make sense? Let's try a couple more examples together. I've got another carbon compound here. So carbon first, I just write carbon. Then I look at what's coming next. I've got chlorine. I change the ending to "ide", so carbon and chloride. To tell you I've got 4 of those chlorides, it becomes carbon tetrachloride. These last 2 make for a really good example for why we have to be number specific. I have 2 compounds, both made of nitrogen and oxygen. So if I simply said nitrogen oxide, how would you know what I was talking about? The first one, NO2, is somewhat of a pollutant, not very good for us. The second one is good old laughing gas, so quite distinctly different compounds. We've got to be able to name them distinctly too. The first one, nitrogen first, the name stays the same. For oxygen, change the ending to "ide", and there's 2 of them, so it becomes nitrogen dioxide. For the second one, the nitrogen and the oxide are the same, but now I've got 2 nitrogens, so it becomes dinitrogen oxide. So, comfortable naming simple covalent compounds? We'll leave it there for this topic. In the next topic, we're going to explore how we build and how we draw these covalent compounds.